Hello everyone, my name is Sophie and today I'm joined here with Neil. And today we're going to be talking about what AI can and can't do. So Neil, my first question for you is, what is AI?
That's actually a very good question. And I'm sure you've noticed, Sophie, that this year every medical device seems to be claiming it's got some form of AI in there. Actually, last year they were claiming that they had some form of software in there or some form of app. This year it seems to be the buzz term is AI. But there's a problem here, so let me just digress a little bit and say what I think the problem is. If you've got a normal medical device that's out there on the market already, what you've done is a benefit risk assessment. And I like to think of this as a level where you have the benefit on the left and the risk on the right. Now, what actually happens normally is you assess the medical device and you determine that the risk is lower than the benefit. You've got a positive benefit risk assessment. What happens when you start introducing AI is all of a sudden you're introducing more risks that's coming from the fact you've maybe got a bigger battery than you had before, that's coming from the electronics, maybe coming from the fact you're now connected via Bluetooth and onto the internet and through the cloud to a processing engine, that you've got something happening on a server that's out of your control. Very small but definable risks, and that's brought your risk level up. And now you've got a marketing group who's so frightened of terrifying people with their new buzzword, AI, they're saying, oh, but really, a clinician is always going to review this, and it's going to be a very senior clinician with 20 years experience. So what we suddenly find is that the risk's gone up and the benefit's gone down. And we've now got a negative benefit risk assessment. The benefits don't outweigh the risks, and we shouldn't be using the medical device at all. We've suddenly made a perfectly viable medical device not approvable simply because we've gone and introduced the latest buzz term, and that's affected the perceived benefit risk assessment. So that was the first thing I wanted to say. There are a lot of things we've done traditionally in software, because software is very good at doing the same sort of things AI is very good at. It's very good at doing a lot of mathematical or statistical calculations very, very quickly. And if we do not just one algorithm, but many algorithms very, very quickly, this is when it starts to give the impression of intelligence, and we can genuinely call it artificial intelligence. So if we've just got a single algorithm that learns from its mistakes, perhaps one that guesses whether a ball on a roulette wheel is going to be coming down in red or black, and it keeps on trying red, and then it goes, well, actually, maybe we can try black every now and again, and it starts getting better, and you perceive it's beating the odds, but it's playing an algorithm. It's got an algorithm that it's running, and it's learned. So that is a very basic learning algorithm. Now, what we can have is, if this is learning off a defined database, and there's a bit of bias in this roulette wheel, it's going to learn to compensate for the bias in that roulette wheel.
Right.
It's then going to work on that database very well, and it's going to fine tune itself to that database. And then if we put that out into the real world, it's going to assume every roulette wheel is as slightly fixed as the one in Sophie's casino. So that what we really want is something that isn't fixed but is adaptive in the real world. So it doesn't just adapt to Sophie's casino real world roulette wheel. It adapts to everybody's roulette wheel, every different roulette wheel. So then we're talking about something that is a variable algorithm, or sometimes we call this an adaptive algorithm. It adapts to the real world situation that it's in. With a medical device, this may be a particular patient population that a hospital has, or a particular piece of diagnostic equipment, a particular piece of hardware that a hospital has, and it manages to say, I'm going to do the best in this circumstance, and it just starts to move slightly its original programming to adapt to the new situation. And this is starting to get where we show something that's like real intelligence. And if we now look at not just including a single parameter, but many parameters, so you're calculating many things, you're making many statistical calculations all at the same time. And that's what gives the appearance of intelligence, because it's doing a lot of things in real time, much faster than a person can do it.
So, some very interesting points you've made there. Now, for my next question is, why AI?
Okay, so I think you really say, what's it good for? And this is where we need to really have a more educated population. So you can, if you try using a chatbot, something like ChatGPT, what you'll find is you can really confuse it, because it's looking at the internet as a whole. It's using the internet as a whole as its database. So it will answer the question that you ask it based on the prevalence of data on the internet. So what is AI good for? It depends a lot on the database that you're training it on, and an appropriate database. So if you're training it on NASA information, it'll give you the answer, Neil Armstrong was the first man on the moon. But if you're training it on all the rubbish that's on social media, on the internet, it'll say, actually, we don't think anyone's ever been to the moon. Nobody was the first man on the moon. So when we say, why AI? What can we use it for? What's it good for? It's very good at making a lot of complex, maybe statistical, maybe other sorts of mathematical calculations very quickly. All software is good at doing that. AI is just an extension of this to calculate a lot of things very quickly using the power of big data to give us insights that appear slightly magical, because we're calculating a lot of things very quickly and taking our line of regression, our best fit curve through those things to say what we think the answer is. However, it depends on the data we give it, rubbish in, rubbish out. It also depends on asking precisely the right question. And it's the same idea with AI. It may give us a rubbish answer because we don't really know the question that we're trying to ask it. We can't phrase the question precisely enough. So, two key things where AI is going to be very bad. It's where we can't precisely phrase the question and where we're not telling it a reliable data set from which to draw that question.
So Neil, one of the things you said previously was rubbish in, rubbish out. So basically you mean data quality. Would you be able to expand further on this for me?
Yes, of course. So today I've got on a couple of watches, and I've had these both as fitness apps, health apps, running apps for probably with their predecessors about 12 years now, something like that. So I've built up about 12 years history of my running data. And look, I've got my Park Run shirt on today just to prove that I really do park run occasionally. So I've built up this little bit of history. I've got a data set over 12 years. And if I look at it, it's telling me something that intuitively I know is wrong. It's telling me that I run faster now than I did 12 years ago. Now, there are a number of things that are playing into this. Firstly, the quality of the fitness tech I had 12 years ago wasn't anything like as good as it is now. I had a very simple wristband that was supposed to be monitoring my number of steps. Now I've got a couple of watches which are also monitoring my heart rate, are also making an assumption about my pulse, my breathing. I've even got an Apple Watch on this wrist that will monitor a lot of other things and give me beat to beat information on my heart, and will estimate my oxygen level and various other things. More than that, the actual step count that it does, it's become much more accurate. So originally, I started off with one of these Nike wrist straps, which would always overestimate how quickly I was running. So it made me feel good about myself, and it made me feel good about recording it on that wristband. So what am I actually saying? If you look at that data that's been compiled over 10 years, it's telling you a trend that is the reverse of the trend. I'm 10 years older than I was. I will have slowed down a little, and I know I've slowed down a little. But the trend of my health data, of my fitness app data, is actually saying that I've increased a little bit. And I know that's just because we've got more accurate information than we had originally. So that's something talking purely about a fitness app. But the same is true for perhaps a diagnostic piece of equipment that we have in a hospital. What we're doing is that we are using old data, and we've got to use data that's about 10 years old, because otherwise, how do we know that we diagnosed the patient correctly? So if we want to make a diagnosis now, we need to know what we were doing, what these parameters said 10 years ago, so that we can now work out with our AI what we would have diagnosed using the new AI, and how the 10 years actually developed for the patient. But the AI we're going to be producing that's tuned to this data set that's 10 years old needs to work 10 years in the future. And maybe we're still going to be making the piece of equipment 10 years in the future. It needs to look 10 years further in the future. So it may be that it's been set up on data that is 30 years old. And 20, 30 years ago, we had very different views about what was a good sample from a patient population. We maybe talked about ensuring there was an ethnic balance. We didn't always talk about ensuring there was a male-female balance. We certainly didn't look at people's sexuality and ensuring that we were truly representing the real world. And most of the old data that we have, the old healthcare data, is predominantly about white males. So data quality is everything in determining where we're going with AI. And data quality is something that perhaps we don't get very easily from an old data set. It's the best data that we have available, but it's not good enough for today, let alone in 20 years' time. So the AI can only ever be as good as the data set that is trained on.
Thank you for that answer, Neil. Now, 10 years is a long time, and a lot can change in 10 years. Do you think this caused any bias?
Absolutely. A lot of the best available data we have at the moment has got this implicit bias in there. And it wasn't deliberate. We thought it was good at the time. We thought we'd taken care of getting the right ethnic balance, but there were a lot of other things that we didn't think about and we would think about today. So yes, the older the data, the more we're likely to find it's implicitly biased. The more we try things out on people within the company, on software engineers, the more we use them as our guinea pigs for developing the data, for developing the algorithm, how things work, the more we're likely to be programming in a white male bias. We're still doing that to a significant extent. So yes, it's all about the data quality and understanding that we may implicitly be programming in bias.
Many valid points there, Neil. Can I now get you to explain to me and the audience verification versus validation?
Yeah, this is a really interesting one for software because we talk about software validation very often, but what we're really doing is software verification. So let me explain the difference. Verification is proving something meets a specification. It's basically answering the question, did I design it right? Validation is about asking whether it's fit for purpose, regardless of whether it meets the specification. Does it do the job we intend it to do? And for medical device AI, does it provide the useful clinical information to the clinician that we want it to? Or is it just providing something that's interesting because we can calculate that, but it hasn't really got any clinical utility? It's not telling us anything. It's not helping us with a diagnosis or determining a therapy. It may actually be confusing the issue. So what we need to do with AI is not just determine that it's making the statistical calculations or the other calculations, the algebraic calculations that we intend it to do. It's not just executing some sort of learning algorithm. What it's actually doing is something a little bit more than that. It's executing an algorithm which is giving information to a clinician which is useful in making their diagnosis or determining the therapy.
Now, following on from that, Neil, how would you say we validate AI medical devices?
Okay, well, the first thing we can do is we can say, well, why don't we just treat AI as a black box? We know the inputs that go into that black box. We know the algorithm, what it's trying to measure, and we know what comes out the other end. We don't really need to understand too much about the AI, what's going on inside that black box. We can treat it as a black box if we've got an awful lot of data that says we put the data in, we see what comes out is what we expect, and we find that has a clinical utility. So that gives us a black box method. But we can actually do a bit better than that because we've already developed a lot of tools for looking at processes and for doing process validation. An AI is just a process that is going on in this black box. So we can start looking at statistical process control. And what that says is we've got an expected value, a mean value, and we can set lower and higher warning limits, and we can set lower and higher action limits where we would actually stop the process. So we set boundaries within which the process can fluctuate. So maybe think of this as something like heating up a flow of material. So what we do is we start off with a single data point. We turn up the temperature perhaps a little bit higher than the mean because we know material is going to be flowing through and taking energy out. Over a fairly short period of time, that will drop and start to even out. Drops and starts to even out, but it's still running maybe a little bit higher than the mean. Maybe we heated it up a little bit too much in the beginning. So maybe now's the time that we say, okay, we can look at where that's running on the graph. What we're going to do is just turn down the heat one notch from number 8 to number 7. And when we turn down the heat one notch from number 8 to number 7, we might suddenly find that the temperature drops much more than we expected. Instead of being near the mean level and slightly above it, we've now gone to only being slightly above our warning level. And maybe worse than that, we're now no longer supplying enough energy into the system to counteract the amount of energy we're taking out of the system by heating up the material. And so not only has the temperature fallen to near the warning level, but it's starting to decrease. And what we do with statistical process control, what we do with things like the Toyota production method is we start saying, okay, so we're using a statistical process control here. We can see this trend is starting to go wrong. What we need to do is to take some action, and we take a predefined action that says, oops, now it's running a bit too cool. We need to boost the level of heat going in. And so we start to adjust it so it comes back into its near steady state running running condition and we refine it. That's talking about a statistical process control process. Now, if we're only looking at one parameter, which is heat, I can do that as a machine operator. But if we're looking at multiple parameters, perhaps heat, the energy going in, perhaps also pressure, perhaps the speed at which the material's going through, we very quickly get above what I can stay on top of as a machine operator if there's a bit of inherent variation in the process. This is the sort of thing that AI is very good at, because it can do the calculations and the statistical projections very much more quickly than I can even use a simple tool like plotting it on a graph and taking a visual look at it to work out what's going wrong. It can really fine tune the process to get it running along the mean much more quickly than I can do that as an operator. But again, it's just a process, and we can look at it running inside a black box to a predefined set of parameters. And if it starts tuning itself to that machine, maybe we're doing this through what we can term a predefined change control plan. And this is one of the ways that we can start to look at validating AI. But I know, Sophie, that's something that we're going to talk about next week.
Now, Neil, that brings us to the end of our discussion today. I thank you for giving us such in-depth responses to all my questions. And we look forward to seeing you all next week when we will be talking about regulation in the UK, US and Canada.